So in this lecture, I will be talking about types of dynamical systems. And I will still focus on two-dimensional flows. We already addressed this when we were considering two-dimensional maps. And it's pretty much similar story with similar conclusions. So we have two-dimensional flow, let's say. The only difference here, we know that here we don't have no chaotic solutions. So we don't have chaotic solutions in one-dimensional flows and two-dimensional flows. Later on, I will show that in three-dimensional flows, we already have chaotic solutions. And this story about types of dynamical systems, it's also can be extended to flows of any dimensions. And therefore, for three-variable flows and above, for 3 and 4 and above dimensional flows, this story about types of dynamical systems is more important because it gives some clues about whether we can have chaos, whether we have chaotic solutions there or not. Nevertheless, even for two-dimensional flows, it makes sense because in two-dimensional flows, we can have, let's say, two kinds of stationary solutions. It is equilibrium and limit cycles. I didn't talk about limit cycles a lot, so hopefully I am planning to talk about limit cycles a bit more in week 12 material. So here my main focus is to provide you with all information for your last homework. So we know how to find equilibria. Equilibria are roots of algebraic system, f equals to 0, g equals to 0. And we know how to analyze stability of equilibrium. So we just find Jacobians at equilibrium and find eigenvalues for Jacobians. And then based on the eigenvalues, we can conclude on what type of equilibrium we have in this system and which of them are stable. With limit cycles, it's far more complicated. It is very rare case when we can derive analytically, we can find analytical expression for limit cycles. We can find them analytically. Usually it's not the case, and there are many ways, indirect ways to find limit cycles. One of them sounds like this. It's based on Poincare-Benedictson theorem. If we can prove that there are bound solutions, for example, we have bound solutions and no stable equilibrium. And from 1 and 2, it follows that we should have stable limit cycle. It is one way to do it, but this, if we have, for example, stable equilibrium, and then we should look at what is going on around, or let's say we can definitely have unstable limit cycles there. And it's very hard to find out if we have the unstable limit cycles. And even we still can have stable limit cycles, and it takes some further analysis to find stable limit cycles. This is one point. Second, it is not always easy to show that our solutions in some area, for example, are bound. So this is another challenge. And anyway, so this all this story gets easy when we can analyze dynamical systems in terms of convergence or divergence of phase trajectories. Or more generally, we can look at trajectories originated. Let's put it like this. So we have this phase plane. So we started somewhere here. And so this is a point. And then we consider all trajectories starting in neighborhood of x0 and y0. And one of questions would be what happens with this area. So if all points from this domain A have, we can find phase trajectory for each of them. And this means that at any next time, this domain is changing. So it changes shape and changes area. And the question is, what happens with area? If area is decreasing, then we have some convergence of trajectories, nearby trajectories. And this may indicate that there is a limit cycle. For example, it can also indicate there are stable equilibria, stable node or stable focus. And these types of dynamical systems are based on consideration of dynamics of this area A. To simplify this system, what I will do, I will consider rectangular area. So we have some point, x0, y0, and I will consider a rectangle. So this, let's put it like this. So this point x0, y0, this point x1, y0, and this point is x0, y1. Then this area A at A node, let's say times 0, is x1 minus x naught times y1 minus y naught. So this is area of rectangle. And what we can do, we can find out how this area changes over time. And so what we're doing, in fact, we're considering phase trajectories which are originated at these three borders. This corner x0, y0, x0, y0, x0, y1, and x1, y0. Then in course of time, these points move, and this means that our rectangle is also changing. In first approximation, it's easy to show that we can keep considering it as rectangle, and then we can use still formula for rectangle, but this area will be changing like this. So this will be, so we use product rule, it will be d derivative of x1 minus x0 divided by dt times y1 minus y0 plus x1 minus x0 times derivative of y1 minus y0. And let's consider this derivative d x1 minus x0 over dt. This is x1 dot minus x0 dot. And x1 naught is f of x1 y0. So this is how x changes at this point. And minus f of x0 y0. Yeah, so this we use definition of definition of our dynamical system. X dot equals to f of xy and y dot equals to g of xy. So now if this rectangle is small, we can use linear approximation. Let's say here what we use x1 minus x0 by absolute value much smaller than 1. Then we can say f of x1 y0 equals to f of x0 y0 plus derivative of f over x at x0 y0 times x1 minus x0. So all of this is linear approximation for this. Minus f of x0 y0. So and this we see this cancels. We'll have derivative of f over x at x0 y0 times x1 minus x0. And similarly, we can find that dy1 minus y0 over dt will be equal to derivative of g over y times y1 minus y0. And now we can conclude on this. So we can say a dot derivative of a over time will be equal. So first term is derivative of f over x times x1 minus x0 times y1 minus y0. Derivative of f over x x0 y0 times x1 minus x0 times y1 minus y0. And second term, this term, so it will be derivative of g over y at x0 y0 times x1 minus x0 times y1 minus y0. So we know that this is a naught. This is a naught. So therefore, or we can say it is a. Let's say this is a. Therefore, this will be equal to derivative of f over x at x0 y0 plus derivative of g over y at x0 y0, and all of this multiplied by a. So derivative of a equals to trace a dot equals to trace of Jacobian at xy times a. So this is our formula on how area is changing over time. And from here we see that a dot is some factor times a, and if this factor is positive, a dot is positive, therefore a is increasing over time. If this factor is negative, then a dot is negative, therefore a is decreasing over time. And from here we conclude, we draw our conclusions. If trace J is positive, then we have area expanding dynamics. And this means generally that our phase trajectories diverge, and this means that our solutions most likely are unbounded. If trace J is negative, then we have dissipative system. And from here we conclude that we should either have stable equilibrium, or at least one stable equilibrium, or stable limit cycle. And finally, if trace G equals to 0, this is called conservative system. So area preserved here, and we can't conclude on existence of stable solutions, stable equilibria, or stable limit cycles. So this term dissipative and conservative comes from physics. So dissipative comes from consideration of systems with dissipation of energy. So it's systems with friction. And conservative means conservation of energy generally. So one more last point is trace of Jacobian. So if we introduce vector field f of xy, let's consider the vector field. It has two components, f small of xy and g of xy. Then for this vector field, we can introduce divergence. Divergence is a dot product of double operator with f. And this is exactly equals to trace of Jacobian. Trace of Jacobian. So this is so what we can say and conclude that everything depends on the sign of divergence of vector field F capital. Now, as you remember, similar analysis for maps was indicating that that classification of systems of maps is defined not by trace of Jacobian, but by determinant. So determinant by absolute value should be, if it's less than 1, it's a dissipative system. More than 1, it's area expanding, and 1 it's conservative. So this was one difference. And second difference, as I noted before, in two-dimensional maps we can have chaotic solutions, and this makes more important this classification of dynamical systems. In two-dimensional flows we don't have chaotic solutions, but for 3D all these considerations, including trace of Jacobian, they are applicable for example, three-dimensional flows. And there it makes more sense because it is more important on analyzing chaotic dynamics, existence of chaotic dynamics.